today we're going to be talking about the Milky Way Galaxy, which is the galaxy that we live in. But first we're going to finish some of the remnants that are left over when stars die, and there will be a couple interesting topics that we haven't covered, and how we can combine gravitational waves and electromagnetic signatures into what we call multi-messenger astronomy. So some of those events that we'll talk about are called gamma ray bursts. So gamma rays are the highest energy photons, so these are very energetic explosions. And we'll talk about what happens when very dense compact objects merge, like neutron stars and black holes. So gamma ray bursts are these very energetic explosions. They can have different progenitors or different causes, but after whatever explosion mechanism has happened, there will be this very intense release of energy in the form of gamma rays. But there will also be a lot of material, matter, that is ejected from the central engine. And this matter will interact with the interstellar medium and will produce what's called an afterglow. So this material that's being spewed out is in a fairly narrow jet, and the material is being flung out at relativistic speeds. So we have to use special relativity in order to describe the behavior of this material. When the material interacts with the interstellar medium, it produces all different wavelengths of light, including visible wavelength light and infrared light, which I use to study these gamma ray burst afterglows. The material ejected from the central engine is also not all ejected at the same time, and different shells of material can be traveling at different speeds. So those, if they are traveling at different speeds, they can collide with each other, and those are called internal shocks. So you can have the material interact with the interstellar medium, and that's the afterglow, or you can have it interact with the another shell of material, and that's called an internal shock. And so these are the highest energy explosions that we have to study in the universe, aside from the Big Bang itself. So these gamma ray bursts were first detected in the 1960s, and we generally break them into two different categories. So we have long gamma ray bursts that last for longer than 2 seconds, and short gamma ray bursts where all of the gamma ray energy is released in less than 2 seconds. So there's these two different populations, and we'll see that there are two different progenitors or sources of these different gamma ray bursts. So we were observing these gamma ray bursts for a few decades, and it wasn't until the 90s that we realized that these bursts were actually coming from faraway galaxies. And so if we remember our definition of flux, flux decreases as distance squared. And so if these gamma ray bursts are very bright, and they're very far away, then they have to have extremely high luminosity. So they have to be very inherently bright. And you can see in the pictures here, this single gamma ray burst can outshine all of the stars in its host galaxy for maybe 50 or 100 days. So that's millions or billions of stars in this host galaxy, and the gamma ray burst is brighter than all of those stars' light output put together. So these are very powerful explosions, and we'll see what could possibly power such a violent explosion. We also made a connection between gamma ray bursts and supernovae. So we learned that supernovae occur when a large star reaches the end of its life cycle. It gets to iron fusion, and that doesn't produce energy. It consumes more energy than it gets out, and so the star will blow itself apart in a supernova. So there are gamma ray bursts that are associated with these large star deaths, and these are the long gamma ray bursts. So the reason that you don't always see a gamma ray burst in a supernova is the gamma ray burst is emitted along those very narrow jets that we talked about earlier, and so if you're not along the line of that jet, you're not going to see the gamma ray burst. Whereas the supernova is more of an isotropic explosion, meaning it puts its energy out in all different directions, and so you can see the supernova, but if you're not along the right angle for the gamma ray burst, then you won't see it. So the long gamma ray bursts are from large star deaths, and then it turns out that the short gamma ray bursts are from mergers between compact objects, like mergers between two neutron stars. We've studied neutron stars in binary systems, so you have two stars that form, two high mass stars that form, they go through their life cycle, they eventually turn into neutron stars, and they're orbiting each other. As they orbit each other, they can spiral in towards each other, and as they spiral in towards each other, they emit gravitational waves. So these gravitational waves take energy out of the system, so they're converting that gravitational potential energy into the emission of these gravitational waves. And so this is data of a pair of orbiting neutron stars, and the circles are the data points, and the line is the theoretical curve. So we've detected gravitational waves from a neutron star merger, binary neutron star merger. We did that in 2017, and we were fortunate to also detect an electromagnetic counterpart to that gravitational wave signal. So it's the only time that we've been able to do that. Gravitational wave detectors have been operating for 10 years now, and in the first 2 years we were able to detect this binary neutron star merger, but we haven't had another one since. And so here's an example of what a black hole merger might look like. So you have two black holes that are orbiting each other. You can see how their masses are distorting the space-time around them and how the background stars look. And eventually these two black holes will coalesce into a bigger black hole than either of the two masses that went into it. And so we've been detecting these gravitational wave signals for a long time now. So this is what the signal for a black hole merger looks like. So we have the first ones were detected in 2015, and there's a gravitational wave interferometer in Washington State and one in Louisiana, and they both have this coincident signal, and the more detectors you have, the better you can localize where this gravitational wave source happened in the night sky. So we've been detecting these things for a while now, and we've built up this kind of population of different masses for the things that created the gravitational wave and what object is left afterwards. So we can see the black hole masses. So the two most massive ones we've detected are both around 80 solar masses, and when they combined, they resulted in a large black hole about 160 solar masses. And then there's also neutron stars that merge, and there's this interesting gap in the mass ranges. So remember, you need to have kind of a higher mass in order to collapse into a black hole, and you need a kind of low mass in order to stay as a neutron star. So there's this mass gap, and we can see there's actually some objects, which are the question marks in the figure, that are actually in this mass gap range. So we don't exactly know what these things are. Maybe these are the quark stars that we mentioned previously that could be held up by some kind of subatomic force. So gamma ray bursts, we can get them from massive star deaths, or you can get them from neutron star mergers. And in addition to a gamma ray burst, when neutron stars merge, you can get gravitational waves. So it turns out if you can pair the gravitational wave signal with an electromagnetic radiation signal, you can do some interesting science. So you can use that to probe the rate of expansion of the universe, for example. So this is another way to study the evolution of the universe. And you can get gravitational wave signals also from black holes merging. So that's kind of the end of our exotic remnants of dying stars, and now we're going to talk about our galaxy, the Milky Way. So from the Earth, the Milky Way is this band of light that you can see across the sky in a dark sky area. The image in this picture is not what you would see with your eye. This is a false color image, so they've taken pictures in different filters and added them all together. With your naked eye, you would see what basically looks like someone spilled milk across the sky. So that's why it's called the Milky Way. This diffuse band of many, many stars all together, and what we're actually looking at is we're looking through our own galaxy out into space. We've also seen that space is not really a vacuum, and there's actually a lot of gas and dust that make up the interstellar medium, and those are kind of the black or the dark clouds that you can see in this image blocking some of the starlight. So if we could look at the Milky Way Galaxy from the edge, we might see something like this. So it's much thinner than it is wide. So the thickness of the disk of the galaxy is maybe 1,000 light years, and its width is about 100,000 light years. So there's this disk, and the sun is in the disk of the Milky Way Galaxy. We're a little more than halfway out from the center. At the center of the galaxy, there's this large bulge, and there are the Milky Way has a halo, so there's these clusters and objects that are orbiting the galaxy, and these are the globular clusters that we've talked about in the past. So remember, there's open clusters and globular clusters. The open clusters are the smaller and younger clusters, and the globular clusters are the older clusters made up of thousands to maybe millions of stars. So if we could instead look at the Milky Way instead of edge on, if we could get a bird's eye view or from the top or bottom, this is what we might see. So we can still see the bulge in the center, we can still see the disk, but now we can make out the spiral arms. So we'll talk more about what exactly the spiral arms are later. And how do stars and clusters move about the galaxy? So stars in the disk, like the sun, they do generally orbit in a circular or elliptical orbit around the center of the galaxy, but they also have this kind of undulating up and down motion. So if a star gets a little bit of extra velocity, let's say up out of the plane of the Milky Way, now it's above the plane of the Milky Way, but most of the mass of the galaxy is in the disk, so it's going to have some gravitational pull pulling it back down. So the star will be attracted back towards the center of the disk, but it'll overshoot a little bit and then be below the disk. Again, it'll be gravitationally attracted back towards the disk, and it'll do this repeatedly, missing and overshooting the disk and undulating back and forth, up and down. So the other stars orbit differently. So if you're in the bulge at the center, you'll orbit kind of in all directions, and same with the halo stars. They won't orbit in a single disk. They'll have these kind of random elliptical orbits. For the sun to do its orbit around the Milky Way, it takes about 230 million years. So if the Earth is 4 billion years old, then we've already been around the center, around the galaxy several times since the Earth formed. So why do stars in the disk bob up and down in their orbit? Yeah, so it's because the gravity from the stars in the disk pulled them back down if they happen to go above it or below it. So it turns out we can measure so if we remember back to Kepler's laws, if we know the period of something's orbit and we know how far it's orbiting, then we can calculate the mass that's responsible for that orbit. So if we do that with the sun, it turns out that there's 10 to the 11 times the mass of the sun within the sun's orbit around the Milky Way. So that means if all of the stars had the mass of the sun, there would be 10 to the 11 of them within the sun's orbit in the galaxy. Of course, there are different masses of stars, but there are a lot of stars and a lot of mass in the galaxy. So to calculate that, we can start with Kepler's law and just rearrange the equation a little bit. So we end up with this mass term, and that subscript of r is just telling you this is all the mass in a given radius. Then we can put in the radius, say, of the sun's orbit, and then to get the velocity of the orbit, we can take the radius, calculate a circumference, and divide that by the period to get a velocity. And then the capital G is just the Newtonian gravitational constant. And so when we do this for all of the stars in the galaxy, we get this graph. So what you would expect to happen is, as you are kind of in the bulge of the galaxy, the central bulge, you would get your velocity would increase a bit as you go out from the very center, as there's more mass within your orbit. And then maybe as you hit some of the spiral arms, you might get another little boost of velocity. But for the most part, as you get further out from the center of the galaxy, your velocity should decrease. So that's what we see in the solar system. So the inner planets orbit much faster than the outer planets do. And so that would be this kind of blue curve. But instead, what we actually see is that as you get farther out from the center of the galaxy, the stars towards the edge actually start orbiting faster and faster. So there has to be a lot of mass that is out at the edges of our galaxy that we're not accounting for. So this is the first evidence of dark matter that we've talked about in this class. So there has to be some mass that we're not accounting for. So it's dark, we don't think it's emitting light, and it's causing the galactic rotation curve to, instead of decreasing, it's actually increasing. So there's this dark matter spread all throughout the galaxy, and there's even a lot of it out at the outskirts of the galaxy. And we'll talk more about dark matter in an upcoming lecture. So to review, our galaxy has a disk, there's a bulge in the center, and there's a halo of stars and clusters that are also orbiting the disk of the galaxy. And the stars in the disk all orbit in the same direction, but they have these little up and down motions due to gravity. The halo and the bulge stars orbit in random orientations. And there's a lot more matter in the galaxy than we can observe, and so we call that dark matter. Okay, so now we're going to talk about how gas is recycled within our galaxy. So we start with a cloud of gas in our galaxy, mainly made out of hydrogen, and then something causes that cloud of gas to start to collapse, and you get star formation. The star will evolve on the main sequence, and eventually at the end of its life, it will recycle that material back into the interstellar medium. So for high mass stars, it'll go supernova, and for a low mass star, it will puff out its material in a planetary nebula. And then that material will be used to make the next generation of stars. And so this material might not necessarily be injected into the disk of the galaxy, but it could be kind of form a plume above or below the disk of the galaxy. And so you get this hot gas kind of blowing out of the top of the galaxy in this picture. Eventually, some of that, as it expands, the gas will cool, and as it cools, it will fall back towards the disk due to the gravitational pull of all of the stars and gas in the disk, and then that material can be used to make the next generation of stars. And so if we look at this cloud of gas in the constellation of Orion, will be mostly made out of hydrogen. There will be about 28% helium, a little bit of carbon and oxygen, and then a few other molecules. So that's what will make, that's the building blocks for what you can make your stars out of. And so this is a star-forming region. So you can see all of the gas and dust that is available to make the stars. But as the stars start to turn on and do their fusion reactions, they're going to blow away any kind of loose, not dense material. So you can see kind of the tips of these nebulae are too dense, so maybe there's a star that's currently trying to form there, and so it's dense enough that it's retained its material from the nearby stars that have turned on and started blowing the material away. And so you get these very pretty images. Of course, these are false color images, so this might not be what you would see with your naked eye, but we've taken pictures and a lot of different filters and combined them all to make this really pretty image. So when you have stars doing fusion reactions in their core, they're turning lighter elements into heavier elements. And so over time, generations of stars will make heavier and heavier elements. And so one generation of stars will have a different chemical composition than a later generation of stars. So we'll come back to that idea when we talk about the evolution of the universe and different populations of stars. So once the star dies, it will blow all of that material back out into space. That gas will go on to form the next generation of stars, and the cycle will continue as long as there's gas to make stars. And if you look at the Milky Way Galaxy in different wavelengths of light, you can see different behavior and different stages of star formation. So invisible light is maybe the least interesting wavelength range to look at. So a lot of the view of the galaxy is blocked by all of the dust and gas that's in the interstellar medium. But if you start looking in infrared light, you can start to see some of the hot gas that is, for example, blown above and below the disk of the galaxy, and that will eventually fall back into the disk and start producing the next generation of stars. X-rays also allow you to see hot gas above the disk of the galaxy. Radio can show you different chemical signatures, for example, for atomic hydrogen, which is what we are going to make most of our stars out of. And then you can also see some molecules like carbon monoxide, and those will be present in the molecular clouds that are going to be forming stars. Gamma rays will show you kind of the opposite energy range. So this is where very energetic stuff is happening. So maybe this is where supernovae are happening. This is where stars are dying and repopulating the galaxy with their dust. And so where did these stars form in the galaxy? There are different types of nebulae that are indicative of star formation. So ionization nebulae, in order for gas to be ionized, there has to be a source of energy. And so when a star turns on, it's going to heat up the gas and dust around it. And you can see different colors that will be generated by different types of ionized gas. So some of these greens and blues might be from ionized neon or doubly ionized oxygen. And And then some of the redder colors might be from ionized nitrogen or ionized sulfur. There are reflection nebulae, so these have kind of more of a blue color. And so why did these look so blue? It turns out it's the same reason that the sky appears to be blue on the Earth. So let's see if you remember why the sky is blue on the Earth, and then you can explain why these reflection nebulae look blue. Yeah, so the reason that these reflection nebulae are blue and the reason that the sky is blue on the Earth is that the blue light is scattered more than the red light. And so while the red light from this nebula might come straight to us and we would see some of that red light, the blue light looks like it's kind of coming from all directions of the nebula, and so the nebula will appear more blue than it does red. So where do stars tend to form in the Milky Way Galaxy? So those ionization nebulae and those reflection nebulae are going to be where stars are forming. And for the most part in the Milky Way, star formation is happening in the spiral arms. So the spiral arms are not like a physical structure that stars are attached to. They're just a kind of a representation of where the stars are forming. So these kind of waves of different star forming regions are what make up the spiral arms. And so there's lots of gas in the galaxy. These clouds of gas are orbiting the center, and as they move around, they're going to be interacting with, basically, they're going to be interacting gravitationally with all the other mass in the galaxy. And so if they pass by a region that is a little more dense, then they're going to get squished or squeezed or stretched. And when we talked about star formation, we said we needed some trigger to cause our gas cloud to start to collapse. So this is one of the ways that you can get a gas cloud to start to collapse. It's just by the interaction with other material as it's orbiting the galaxy. Some nearby material in one of the spiral arms can trigger the star formation. And so that's why we see most of the star formation happening in the spiral arms, is because that is the region of kind of more density within the galaxy. So we get this recycling of gas by the stars forming, eventually dying, and putting their material back out into interstellar space. And in our galaxy, the star formation is going to be happening in the spiral arms, and that's where the kind of more dense regions of the galaxy are. So we said that there are kind of the stars in the disk of the galaxy, there's stars in the bulge, and then there's stars in the halo of the galaxy. So what can we learn about the galaxy and the history of the galaxy by studying these different populations of stars? So the stars in the disk are typically the younger stars. There's some old stars mixed in, and they have compositions like the sun. So they are, if you look at the metallicity of the sun, then the metallicity of the other stars in the disk of the galaxy will be the same. If we look at the halo, it turns out that these stars are actually much older stars, and they have a low metallicity, so they have not very many heavier elements. So we'll talk about this again next lecture, but when you see a star that doesn't have a lot of heavy elements in it, it means that it formed very early on in the universe when previous generations of stars hadn't had a chance to convert a bunch of hydrogen and helium into heavier elements. So this is a video of kind of the formation of galaxies in the very early universe, and we'll come back to more of these kinds of simulations. Maybe I'll speed this one up. So you can see the disk forming, but each galaxy is not really on its own, and you can see they'll interact and merge with each other. And you can have collisions between even bigger galaxies. And this is something that we'll keep in mind when we talk about the fate of the universe and also the fate of the Milky Way Galaxy. But it's very similar to the formation of a solar system. So you get this cloud of gas, something triggers it to start collapsing. Due to the conservation of linear momentum, it'll flatten into a disk. And then conservation of angular momentum makes everything spin in the same direction. And in this case, you are left with a galaxy, and then within the galaxies, you get clouds of gas collapsing further to form planetary systems or stellar systems. So for the Milky Way, the halo stars are the older stars, and the disk stars are the younger stars. And a galaxy will form and follow the physics much in a similar way that the solar system formed. Cloud of gas starts collapsing, conservation of momentum makes it flatten, conservation of angular momentum makes everything spin in the same way, and you get a galaxy to form. So that was the halo stars and the disk stars, but what can we learn by studying the stars in the central bulge? So when we look at the center of our galaxy, there's not like some big star that everything is orbiting, but we do see things like X-ray flares and intense radio light coming from the center, but there's no star there. So we can explain the X-ray flares by what's called a tidal disruption event. So if you have a very large black hole and a star is orbiting it and it gets too close, the tidal forces of that black hole can basically shred the star apart. And this will be a very violent process and will lead to X-ray flares. The bright radio waves are due to basically the friction of everything that's orbiting the black hole just heating up enough to emit radio waves. So these are just some indirect evidences that there could be a black hole at the center of the Milky Way. And when we look at some stars that are orbiting the center of the galaxy and we calculate the mass that would be needed to cause these objects to orbit at the radius and the speed that they're orbiting, we get a pretty ridiculous mass. So the things that these stars are orbiting at the center of the Milky Way Galaxy has to be 4 million solar masses. So when I showed you the kind of the family tree of all the black holes we had detected with our gravitational wave detectors, we got up to 160 solar masses. So those are stellar mass black holes. But now, when we start talking about what's at the center of galaxies, these are supermassive black holes. So there's questions as to whether you could build these supermassive black holes starting from a stellar mass black hole. Has there been enough time in the history of the universe, 14 billion years, to basically grow a black hole from stellar mass to supermassive black hole in that amount of time? And if not, then we need to explain where these supermassive black holes are coming from. And so we've actually taken a picture of the black hole in the center of our galaxy. So this is a radio image. So these are this is the accretion disk around the black hole, and then the dark thing in the center is the black hole. So this one was harder to image because, again, we are in this galaxy and there's a lot of stuff in the way. And this is actually not a very big supermassive black hole. We'll see much bigger supermassive black holes when we look at other galaxies. So this is so Sagittarius is the constellation where the center of the Milky Way is, and so Sagittarius A star is the black hole that is in the center of our galaxy. So there's a lot of indirect evidence that there is a supermassive black hole there, and now we've actually taken an image of it in radio waves. So we'll see that there's a supermassive black hole in the center of the Milky Way, and there's going to be a supermassive black hole basically at the center of every galaxy that we study.